present a solution for the International Math Olympiad 1986 problem 1. At first, let's have a look on the problem statement. We are given a positive integer d which is not equal to 2, 5 and 13, and now we have to show that there are two different ab in the set 2, 5, 13 and d, such that ab minus 1 is not a perfect square. If we work with positive integers and some square numbers, it's always a good idea to consider the question in modulo 4, because in modulo 4 we have only two quadratic residues, namely 1 and 0. We can see this because we have that 0 squared is congruent to 0 mod 4, and we also have that 2 squared is equal to 4 is congruent to 0 mod 4, and on the other hand we have that 1 squared is congruent to 1 mod 4, and 3 squared, which is equal to 9, is also congruent to 1 mod 4. So we only have the quadratic residues 0 and 1. Okay, so now I want to make a proof by contradiction. So let's assume that 2 times d minus 1 is equal to x squared, 5 times d minus 1 is equal to y squared, and 13 times d minus 1 is equal to z squared. As I already said, it's a good idea to consider this equation in modulo 4, and therefore we think about d in the different residue classes modulo 4. So we start with the first case, that d is congruent to 2, or that d is congruent to 0 modulo 4. Here we see that 2 times d is congruent to 0 modulo 4, so we have that 2 times d minus 1 is congruent to minus 1, which is congruent to 3 mod 4. And if we have a look onto the left hand side of the whiteboard, we see that 3 is no quadratic residue, and therefore this is directly a contradiction. The second case is that our d is congruent to 3 modulo 4, so d congruent 3 mod 4. And here, if we use our second equation, we get that 5 times d minus 1 is congruent to 5 times 3 minus 1. This is equal to 14, and 14 is congruent to 2 modulo 4. Here we again see that 2 is no quadratic residue modulo 4, and therefore this is also a contradiction, and therefore our only possible case is that d is congruent to 1 modulo 4. From d congruent to 1 mod 4, we can write d as 4 times k plus 1, where k is a non-negative integer. And now we can plug in this d into our two equations here, and we get that y squared is equal to 5 times 4k plus 1 minus 1, and this is equal to 20 times k plus 5 minus 1, which is equal to 20 times k plus 4. Now we can factor out the 4 and get that this is equal to 4 times 5k plus 1. In the same way, we can plug in d into the second equation, and get that z squared is equal to 13 times 4k plus 1 minus 1. This is equal to 52 times k plus 13 minus 1, and this is equal to 52 plus 52 times k, plus 12. Here we can factor out again a 4, so this is equal to 4 times 13k plus 3. Now, since 4 is a perfect square, we know that the second factor in these two terms must also be a perfect square, so we can write 5k plus 1 equals y prime squared, and 13k plus 3 equals z prime squared. Now we can subtract these two equations from each other and get that z prime squared minus y prime squared is equal to 13k minus 5k, which is 8k, and 3 minus 1, which is equal to 2. And now we see that 8 is congruent to 0 modulo 4, so this is in total congruent to 2 modulo 4. But now, if we have a look back onto these four equations here, we see that there are no two quadratic residues with difference 2, and therefore this is impossible, and we are done.